Hi, everyone. I'm Colin. I work at Eventual. We're a company that's building Daft. Daft is essentially a distributed query engine that's going to be replacing Spark, in a world after Spark. Essentially, we're a distributed query engine that's designed for multimodal data. So think images, videos, PDFs, tensors, etc. So I've been working at Eventual for the past 9 months or so now, and I mainly work on our execution engine. So today, that's what our main deep dive will be, how Daft's local execution engine will work under the hood, and I'll be talking about how we optimize Daft for performance and memory.
Cool. And hi, everyone. I'm Desmond. So I used to work Databricks on the Photon engine, which was Databricks' replacement for Spark's execution engine. Now I'm at Eventual. I joined a couple of months ago, and I'm really excited to talk about Spark, how it's so great, and how we're going to build the next technology after Spark. So that's the topic of today's talk, life after Spark, right? Before we go into Spark, I just want to talk a bit about Daft. Daft is a multimodal query execution engine. So what that means, if we break it down, multimodal would be different data types. So it's top of like the regular BI data types like images, like strings and integers, you get machine learning data types like images, videos, tensors, embeddings is distributed. So you can use Ray to orchestrate your workloads. It's fast, and it's going to work on cloud first as well. So it works on all your different clouds. Now we're going to talk a bit more about Spark, right? So what is Spark? Apache Spark is, this is a quote from Wikipedia, it's an open source unified analytics engine for large-scale data processing. And let's break down what all this means, because I know this is a systems meeting, but we're not all like distributed data systems. There's a lot more to systems than that. So first of all, let's talk about analytics engine. Let's say you have a bunch of data, and you want to query this data. In a classic database, what we might call an online transaction processing database, you're going to select a specific row from your data, right? So let's say you have data about your users, you want to find a specific user, and you want to update, say, some detail about this user. Now for analytics engines, these are different, right? You take all your data, and instead of getting a specific row, you're going to operate on columns of your data. So let's say you're aggregating some value, like all the money that all your users have, or like the number of visitors you have for your website, you're going to aggregate across a column. Now let's talk about large scale. For non-large scale, you're probably going to use a single powerful machine with a single disk. For large scale, you're going to move towards distributed workloads. So for Spark, you're going to have multiple executors, parallelizing your workloads, accessing more disk, more I/O, more compute. Now we talk about data processing. A classic data processing workload we show here is called extract, transform, load. What you have is like raw data. Let's say from raw data from JSON, from CSV, from your databases like Postgres. You're going to transform it. Let's say you select part of your data, you perform transformations on it, you aggregate it, and then you store it back. You load it into a data warehouse. What this might look like is that you get, say, an ETL pipeline for a ride-sharing app, right? A ride-hailing app. You take your usage data, you take, say, geographic data, you take data about like profits, you aggregate it, and then you create some visualization for some hotspot of like where it's good to place the ride-sharing apps. Now, what does unified mean in all this? So for Spark, what it kind of means is that you have an all-in-one package, right? You can do machine learning on Spark, you can do graph computation on Spark, you can do streaming on Spark, you can do business intelligence on Spark, you can do governance on Spark. You can do all of this. You can do it through SQL, you can do it through Python, through R, through any programming language, through Spark Connect, really. You can use Jupyter Notebooks, you can use your Visual Studio Code, IntelliJ, whatever you want. So that's Spark. Now I want to talk about why, instead of what is Spark, like why is Spark so great? Why Spark in the first place? And I'd like to paint a little story. So in the beginning, right, there was data, vast amounts of data in silos, unmanaged. And then there was Hadoop, right? Hadoop came along, it was great. It gave us the Hadoop distributed file system, where you get a bunch of distributed storage locations, and you can now store the data. Now you want to process the data, right? You want to run analytics on the data. So then we get MapReduce, where you have all your data, and you have distributed compute. You map data to a single reducer, and you keep repeating this for different computations, and eventually you aggregate some sort of data. Here's some BI graph. Now the problem with Hadoop was that Hadoop had this system where instead of compute talking to compute and just going through in memory, Hadoop will always take whatever result it got, store into disk. The next compute resource would read it from disk and then operate on it. Now, as we know, disk is much lower than memory. So this was actually really expensive. Even worse, if you're doing, like, say, small interactive queries, Hadoop would never reuse computation or memory. It would just read the data from disk again and compute everything again. And so this was really slow. And, you know, we stuck with it for a while. Everyone convinced themselves that it was fine, but it really wasn't. And so out of this fire, came Spark. Right? Spark used in-memory computation. Spark had the resilient data, distributed data set abstraction where they reuse data, reuse computation. It's really fast, it's really great. And so kind of what it looks like is that we had Hadoop, where Spark built on top of Hadoop, and now Spark could read from HDFS. It could also read all sorts of different data types from Amazon S3, Kafka. It could read Parquet, JSON, CSV, databases like Postgres, and sort of like, this is trying to draw a picture of the ecosystem. This might be your data layer, but it could also be your ingestion layer, ingesting from these data sources, and then piping it to Spark. Spark will compute, it will run your analytical queries, it will clean up the data, process it, aggregate it, and then maybe it takes your cleaned up data, stores it back to storage. You get all your different table formats, Delta, Iceberg, you store it back into S3. And then you can even pipe it to all your business intelligence tools, Power BI, your analytics tools like Tableau. This is like a fantastic ecosystem. And because it's so fantastic, and we see that Spark is really a great technology for doing distributed computation, I think the next bit is going to be a bit opinionated. We're going to talk a bit about what's missing from Spark. The screen is tearing. So we think that there are 5 major pieces that could make Spark really great. The first is better local execution, better stability, better out-of-the-box experience, being cloud first, and having better support for multimodal data. Let's break down what this all means. So for local execution, we know that Spark runs on the JVM. There's a lot of resources out there that point to why this is not great. Because even though Spark is a distributed computing framework, you want fast local execution. You want to keep your costs low. You don't just want to keep scaling by adding more machines that are not running efficiently. Databricks themselves have great resources about why the JVM is not the right solution. Spark also relies on partition-based parallelism. This is pretty inflexible, and Spark requires a lot on the adaptive tuning of their queries because of this. And if you combine this with bad configurations, and which are esoteric and which are poor defaults, which is pretty common to Spark, you kind of get stability issues. You combine this partition-based parallelism with bad configurations, and you get an There are a lot of other things that make Spark unstable. For example, broadcast hash join is a very common operation. It's very fast because you kind of broadcast all your data from different compute machines, the executors, to the driver. You create a hash table, you send it back out to the executors, and it's really efficient. But this often results in ooms. Data has a lot of different properties. Sometimes your partitions have different sizes, there's data skew, and this results in ooms. And not to harp on it, but with the JVM as well, people really love to use Spark and PySpark. Problem with this is you kind of use a Python interpreter connecting to the JVM through Py4j. The memory model is not unified, and once again, you get a bunch of ooms. I struggle a lot with this when debugging, a lot of Spark issues, so it's a pain point. And this is not a great experience if you're if you're doing distributed computation, you're munching a bunch of data. You want it to be stable. You don't want to run your job, and then 10 hours later find out that it ooms on some part of the job because you didn't choose the right join algorithm or some issue like that, or you chose the wrong configuration or partition sizes. This leads to a pretty poor out-of-the-box experience. You want the technology to be friendly to users. You want it to feel great to use. So your data engineers will be happy. Your data scientists will be happy. But the problem with like Spark is that it kind of has a lot of esoteric configurations, kind of not good by default sometimes. So you often have questions like, why is my job slow? Why does my job fail? And I think the scariest of them all, why does my job fail only sometimes? Everyone loves Python. A lot of Spark users use PySpark. The problem is you're not really using Python. You're kind of using Java under the hood, and you're connecting it to Py4j. So when you first install PySpark, if anyone's ever done like pip install PySpark, you will try to use Spark, and you will fail because you might not have set up your Java environment properly with your Java home, the right JVM 17. If previously you might have to use like Java 8 or Java 7. Beyond that as well, sometimes you're using Spark and you get an error. By using PySpark, and you get this strange Java error, you don't know what it refers to. This is kind of the user experience using Python with the Spark. And yeah, sometimes you get strange issues, you didn't set it up properly. Another problem with Spark is that, if you go back to first principles, database engines are very fast because they take advantage of data semantics to actually perform the right algorithms, to skip over data, to plan your query execution. This is why you use a database and not an operating system, file system to read data. The problem with a lot of data lakes, sorry, I didn't introduce that term, but the problem with a lot of data that sits in S3, in your buckets, in your databases, in Java and CSV, is that you don't have a lot of statistics or information about it. There's no free lunch. You can't execute a query correctly, so without statistics, you kind of can't do things really well. Another thing that would be really great would be to build for the cloud first, because all of us use the cloud nowadays. Kind of what we see with Spark is that it doesn't support S3 really well. It only supports S3A. And in fact, to go one step further, it only supports S3 through Hadoop, right? Because Spark was built to replace Hadoop, built on top of Hadoop. So you kind of use S3 through Hadoop jar. It's not a great experience, and you kind of also are oriented now for the Hadoop file system, which has very different properties from an object store like S3. It's not efficient. Because of the JVM, Spark also is not really ephemeral for compute. It takes a long time to start up. It's cold to start up, and it's a big problem where you're like scaling up your clusters and scaling down your clusters. So it's not very, like for cloud-based computation, we kind of want to think in terms of cattle versus pets. Pets, where you kind of like lovingly take care of a compute resource, and you bring it up and you keep it around for a long time. Cattle, where you just use it like livestock. You spit it up, you kill it, you whatever. Spark also has a bunch of like very expensive file-based shuffles. It's not really built for the cloud. You see a lot of stability issues with that. And finally, multimodal. BI is great. We all love to see a good graph from our user data. But the world is moving towards ML, is doing a lot of ML data on images, videos, tensors, embeddings. And kind of what we see is that you can do some of this work on Spark, but a lot of the improvements for all the above list items might not be integrated with it. So for example, you write a new vectorized query engine for Spark. Most of the times it won't be connected to new data types like images or videos. You need an ML extension library to use it. They'll use like Python, use something else. It's not going to be fast. And as well, if your engine does not natively support these data types, you have very poor planning for queries on these data types. So for example, if your data sitting as a bunch of URLs in S3, you download images, it's going to explode in size. If you didn't account for this, if you're not aware of these data types, your planning suffers and you get a lot of stability issues. So I've talked a lot about these different aspects. There's one aspect I didn't talk about, which is ecosystem, like what applications kind of connect with it, what catalogs, what connect to your database engine, what can you do with it. I'll leave that alone for now. For now, I'd like to jump into why all these things I talked about, which I think are missing from Spark, we want to address it in this unified engine. We want to, because all these solutions kind of link in together, and really, you can't build up one aspect of, say, stability without improving local execution. You can't be cloud first without improving out-of-the-box experience for your cloud, and they're all related. And today, Colin's going to dive in a lot into how we're building a very fast local executor.
Cool. So first of all, why are we even talking about local execution, right? We just talked about distributed computation, Hadoop, MapReduce, and then now suddenly we're going back to local. But if you think about it, if you're writing an ETL job, what's the first thing you do? You want to write your query. You want to write your query. You want to test it. It's likely that you're not going to test it on a distributed cluster. You're going to test it on a single node. So Spark is not really that good at that. You know, you have to install your jars, install Java runtime, and then write your query. At Daft, we're trying to make the transition easy. We want Daft to be able to be good at local execution and then easily transition that into distributed execution. So the running joke is here. Of course, Spark is slow on 1 gigabyte versus DuckDB. It's meant for 1 terabyte. But we think that a distributed engine should still run amazingly on a single node. No excuses. So let's talk about a little bit about trade-offs between local and distributed. Compute versus memory. If you're running on a single node, you want to scale vertically. If you're running on a distributed cluster, you can scale horizontally. I/O, on the other hand, you're limited on a single node by your I/O resources. So if you're reading a lot of files, 1 million files, for example, from S3, it's likely that you want to go distributed. Fault tolerance, local, no fault tolerance. Distributed, you get fault tolerance. The use cases are also slightly different. On local, you're doing smaller scale ETL, testing, data science, and distributed, that's where you go big for the big data. And just for some engines that are local and distributed, for example, DuckDB, Polars, and Data Fusion are all local engines, and you have Spark and Trino for distributed. And of course, Daft, we're trying to do both. So today we're going to talk about what does great local execution look like for a distributed query engine. 1, it's got to be performant and memory stable on a single node. 2, it has to work out of the box. It means when you do a pip install get Daft and you run your query, that's it. You don't have to do any extra configs. You don't have to add any extra command line arguments. It should work. We want a seamless transition from local to distributed, which means that the query you write on your single node or Python notebook should translate. We also want excellent interactive computing experience. So if you're reading a lot of files for an ETL job and you want to test that query and only see a little bit of that query, that should work snappy as well. So how do we design for a great local execution engine? First, let's go a bit of a background into a little database class. How does a query engine work? So let's take this query, all right? We're selecting some names, emails, performing a join on 2 different tables, and we write that into some other table. So what the query engine is going to do is going to take your query, and it's going to translate into what we call a logical plan. These logical plans are represented as a tree, with each node being an abstract operation that the user requested. From that logical plan, we're going to translate it into a physical plan. So here's where we translate any abstract operations into concrete physical operations. For example, here, we've decided that a hash join is going to be the algorithm that we're going to choose for our join. And this is the part that we're going to get into today. How do we actually take this physical plan and run it to get your results? So to design an execution engine, we've kind of boiled it down to 3 things. How do you drive execution? How do you parallelize your operators? And how do you synchronize your data flow? And we're going to get through these things one by one. First of all, driving execution. And in the database world, there's kind of 2 paradigms for this that people talk about. It's pull and push. So first of all, a pull query. If you're not familiar, or I like to think of it as the DFS model, where you're recursively going down the tree, you're calling your child to get some data from it, and then you process it. In the database world, this is called the volcano or iterator model. And this is usually implemented via virtual function calls on your child to get data. The second paradigm is the push model. This is also called the visitor model or the callback hell model. And yeah, and then so in this model, operators don't wait for their parent to call, give me some data. They receive data from some input buffer, do their own processing, and then push it out to another output buffer. So what are the trade-offs between push and pull? Performance and scalability-wise, if you look at the literature, there's actually not much difference between the 2. They're more just how do you process your plan, which direction do you do it. However, some things are easier in one paradigm than the other. Limits, for example, are much easier in a pull model because it's inherently demand-driven. All the limit operator needs to do is, hey, give me this chunk of data. Okay, I've reached my limit, stop. Sort merge joins are also similarly easy in a pull-based system. Essentially, you're going to be iterating through 2 different sides of the table and then merging them together. However, DAG-shaped plans, or CTEs, essentially where we're reading data from some table, and we're going to use it in two separate parts of the query. For example, something like select star from table, group by, blah, 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 and then join on data from that same table. So in a DAG-shaped plan, in a push-based system, we can easily just take the scan of the data from that one table and push it directly into both sides of the query. So some engines that support the push-based system are DuckDB, Snowflake, and us. And the pull-based system is implemented by Spark and most traditional SQL databases. So next, let's talk about performance. How do we parallelize our operators in a multi-core system? So there's two methods, partitions and morsels. In the partition-driven parallelism paradigm, you create partitioning in your plan. So if you look at a Spark plan, for example, you'll see things like number of partitions, which is essentially how many instances of this operator do I process in parallel. The number of partitions is static per plan, and it requires these things called exchange operators to perform repartitioning. I like to think of exchange operators as like multiplexers or demultiplexers for queries. So here's an example of a Spark query plan where you can see the plan puts in an exchange operator in order to change the degree of parallelism for that query. The other paradigm is called morsel-driven parallelism, and this is something that was created by the Hyper database in Germany. And so in this model, partitioning is dynamic. I like to think of it as runtime partitions. We're reading from a data source incrementally, and we're creating partitions on a chunk-by-chunk basis with a predetermined chunk size. So in here, parallelism is completely dynamic. It's completely determined by your data size, and operators themselves can control their degree of parallelism. Again, trade-offs. Parallelism in a partition-driven model is static. It's determined by the plan, whereas in a morsel-driven setting, it's dynamic, determined by the operator. Load balancing, which is something that Desmond alluded to earlier. In a partition-based parallelism, you could have a lot of skew between your partitions. For example, if you had a filter, right, and one file is really selective on that filter and the other isn't, you're going to have imbalanced partitions between the two. However, in morsel-driven parallelism, there's no skew because morsels or partitions are determined by your size. CPU utilization depends on number of partitions, depends on data size. Engines, Spark and Data Fusion use partitions. DuckDB and us, we use morsels. And the last thing I want to talk about when it comes to designing an execution engine is synchronizing data flow. How does data flow flow through your query? So bulk synchronous, I like to think of it as a step-by-step process. The scan is going to start reading some Parquet file. It's going to read the whole Parquet file, and then it's going to pass it out to the join. The join is going to complete the join, and it's going to give all of its results to the write, which is then going to write everything into file. So each operator is going to complete its own execution before returning its results. In a streaming data flow, no, we're not talking about Kafka or Flink. We're going a bit more low level than that. It's about processing small chunks at a time, incrementally returning results. You can think of it as either returning a big chunk of data at a time or returning an iterator of small chunks. And so in these two models, how do we deal with larger than memory data sets? In a bulk synchronous model, we're not so confident. Of course, determines on the query. It depends on the query, but we're not so confident because in a bulk synchronous model, you're processing huge chunks of data at a time, and that data is going to be materialized in memory. Whereas in streaming, we're processing a lot smaller chunks of data at a time, and therefore we're never fully materializing your data in memory. Peak memory usage is therefore higher in a bulk synchronous model and lower in a streaming model. Performance-wise, depends on your tail latencies. If you have one part of the query that's taking really long to compute, then that's going to affect both a bulk synchronous and a streaming model. And so engines that do bulk synchronous are Spark and Data Fusion. Engines that do streaming, DuckDB and Daft, for example. So now that we've gone through the three different design options, driving execution, how do we parallelize operators, how do we do streaming or bulk synchronous, let's talk about Daft, and let's talk about what we chose to go for. And we have a little pet name for the project. It's called Swordfish, because Swordfish is a fish that's fast. We didn't want like a land-based animal because that's like common, so we decided for some, seafood. Yeah, so we're transitioning from a pull-based, partition-driven bulk synchronous model to a push-based, morsel-driven streaming model. Why? We're optimizing for our most popular workloads, where memory efficiency and fast queries are the priority. Things like data loading into ML pipelines, ETL into cloud-based catalogs, and interactive data analytics. Here, in these type of queries, we never really need to materialize data in memory. It's always streaming from an input, streaming back to another output. And we really need fast queries. For interactive data analytics, you could be reading large amounts of data in S3, but only returning small amounts of data. And we need a streaming execution engine to support fast queries for that. Let's get into some implementation details. No, my slides didn't work. Okay, we'll go with this one. So each query is going to run on a single async runtime, single-threaded async runtime. If you're familiar with Rust, we use the Tokyo runtime for this. So each query is going to run on a single-threaded runtime, and each operator is going to be scheduled as a task. So if you're not familiar with async runtimes, you should think of it as an event loop, and each state of the event loop is like an operator that's going to compute at that time. And so data transfer between operators is via channels. We are a push-based system. Operators push their data into a channel for their parents to receive. In order to parallelize, operators are going to submit tasks to a separate async runtime. And this separate async runtime, or our compute and I/O runtimes, are multi-threaded. And they exist across the process, across queries. And these multi-threaded runtimes are going to be the runtimes that manage our compute resources, memory resources, and I/O resources. I like to think of this analogy as an analogy of a restaurant, right? You can think of the waiters as the query, and the waiters know the orders for each customer. They know what the customers want. And so they're going to submit the orders to the kitchen. And there's limited amount of cooks in the kitchen, similar to how we have limited amount of CPU resources. And so these are going to manage resources across the lifetime of the restaurant. Okay, so we implemented Swordfish. Now we got to test it, right? So we're going to show some benchmarks here. The TPCH benchmark is a set of queries that are supposed to model real-life business queries. It's commonly used across all the database engines. And so we actually see pretty good performance in terms of speed compared to both Spark as well as our previous executor. And the thing that I really like, remember what I said before about streaming execution, right? We're reducing peak memory usage by a lot. And so our memory graph here, compared to our previous executor, on most questions, we're actually getting way better performance in terms of peak memory usage. And so if you're doing, our most popular queries like data loading to ML pipelines, ETL, this is going to be really good for you. So our roadmap to launch Swordfish, we're attempting a end of September beta. In order to do that, just a couple things. Streaming rights and then better statistics. Essentially, we want to be able to predict what your data is going to look like in order to optimize our queries. So yeah, that was today's topic, local execution at Daft. Like Desmond mentioned before, there's kind of 6 pillars that we're kind of thinking about when building Daft, looking back at Spark's deficiencies. Local execution is one. We are really good at Cloud First as well. It's really easy to read data from S3, GCP through Daft. We're multimodal. We support natively image types, embedding types, tensor types, you name it. Really memory stable, as you saw with the memory graphs just now. And we have a pretty good out-of-the-box experience. Our backend is written in Rust, and it's compiled into a binary behind a Python API. So all you really need to do is pip install get Daft, and then run your queries. One thing we're not so good at yet is ecosystem, and that's where Spark got us. They've been around for a long time. They have a really good ecosystem. Us, not so much, but we're getting there. Cool, okay. Yeah, we're hiring. Yeah, a lot of stuff. Systems engineers, distributed query engineers, full stack engineers, and platform infrastructure engineers. So it sounds like you, please shoot us an email. Yeah, we have free stickers, anti-Spark social club, so please come up to us and get the stickers if you like. And yeah, that's it. Thank you so much.